Hi, folks. Good morning. It's 11 o'clock. Let's get started. I'm still missing 3 people. Oh, there's one of them. So before I make all sorts of important announcements, how about let's just do the warm-up. So go ahead and read through the questions. These are only warm-up questions about the material we did together last time together on Tuesday. I realized that on Thursday we weren't here, so I'm not asking warm-up questions about Thursday. I'm asking warm-up questions for Tuesday. So go ahead and read through the list, talk with your neighbor, and then we'll start about 2 minutes. You made it just in time. Literally walked in.
No, I'm just talking out loud.
This is like stuff, like those graphs we did in Homeland Driver.
You will pick up
Yeah. It's a whole one, right?
and then
Like if it's somewhere else.
yeah, no, the ones like you need to do the other one.
The actual answer. It's not on the graph. Then it's sometimes it's like two places.
But there is a
We can cancel it. Got a positive 7 and a negative 7. We can cancel it. Sound effects are very important.
Well, the last one we were doing was like this is back here and the bottom, and then it's like x minus 3, you cancel it out. And that's what.
I feel like also like using I
don't know how to do it.
All right, folks. Like I said, I'm still missing 2 people, but let's review these questions. Hopefully they're here by then, and we can talk about last Thursday and how to move forward. So, when we say a function is continuous, what intuitive idea do we have in our minds? We want to say that it's continuous. That means what? Well, that's true. A curve can keep going, but I mean, this curve, if I draw like a step function like this, doesn't that keep going? Like, is that what we mean by keep going? Like this will just keep going forever, like Stairway to Heaven. Like I'm just going to keep on going and keep on going. That's not what you mean by keep on going. There we go. Yeah, you don't pick up your pencil. So a continuous curve is something that you can draw without picking up the pencil, and that's what we mean by continuous. That's an intuitive idea. Okay, and what are 2 common types of discontinuity? So when we say there's a discontinuity in a graph, what are the 2 common ones that we'll see? Yeah, a hole and a jump. So my curve could be moving along continuously, and then oops, there's a hole. Then it moves along continuously, and then oh, there's a jump. So yeah, you could either have a hole or a jump. And those are 2 different types of discontinuities. And essentially what we say in calculus is we don't bother studying those functions. Right? We want to study functions that are continuous because you need continuity in order to do a derivative or an integral. Well, technically you can do an integral without continuity. But the point is continuity is kind of like the starting point. You need functions that are continuous in order to do calculus with them. Okay, and how do you recognize types of discontinuity in an equation? So like let's say that I gave you an equation, say, oh, I'll just do like x squared plus 7x plus 12 over x plus 3. What problem is this function going to encounter? Like what input am I not allowed to input into this function? Yeah, -3 is no good. I could not plug in -3 right now. If I plug -3 up top, well, that would be, let's see here, -3 squared is 9. 7 times -3 is -21, and then plus 12. If I plug -3 on bottom, -3 plus 3 is 0. And furthermore, 9 minus 21 is -12 plus 12 is 0. I get 0 over 0. So that's a massive problem. And that's how you recognize discontinuity in a function. If there's a value that you can plug into a function that makes it undefined, then you'd say, well, that function's not continuous. Something happens right there. And the thing that could happen there is that it could either be a hole, or it could be a jump, Or one other possibility we didn't talk about is an asymptote. An asymptote is when the function approaches a vertical line and it gets infinitely close but never actually touches. So this would be an example of an asymptote. That thing, or that graph, is just going to shoot up infinitely far, and it's going to get closer and closer and closer to the dash line and never touch it. That's an asymptote. Okay, and then finally, what do you need to do to a function if the output is 0 over 0? If you have a function like this, and you get a 0 over 0, what can you do to fix this function? Well, you factor it. Thanks, Josh. So you can factor the top, and that would become x plus 4, x plus 3, all over x plus 3, and then the very term that was causing part of the problem, namely 0 in the denominator, because keep in mind, 0 in the denominator is the only problem. You're allowed to have 0 in the numerator. 0 can be in the numerator all day long. If I have the fraction 0/5, that just means that of a pizza cut into 5 pieces, I didn't get any, right? So 0/5 is fine, that represents 0. But the problem is the 0 in the denominator, and the problem is the term x plus 3. And by factoring, I take that problem binomial right there, and I cancel it right out, and then I'm left with x plus 4. And now this is an expression where I can plug in -3. If I plug -3 up here, I get 0 over 0. But if I plug -3 right here, I just get -3 plus 4, which is 1. So, yeah, what do you need to do to a function if the output is 0 over 0? You need to either factor it or somehow manipulate it in order to reduce it and get rid of the problematic binomial in the denominator so that you're no longer dividing by 0. Okay. The two people who I thought were going to show up didn't show up. Wait, who do we need? Nando and Devis Wright. Well, I wonder where they are. Well, folks, let's talk. So first of all, last Thursday, I was absolutely devastatingly sad to not be here. I've never, ever not come to a class at Gateway Community College. So that was a big bummer. I want to apologize to each of you personally. I'm sorry that I wasn't here. To make up for it, I stayed late at school on Thursday night, and I recorded myself doing a lesson for you all for just over an hour. Did any of you watch the video?
I could have watched it, but it wasn't showing anything. I forgot to.
It wasn't showing anything? No, wait, did that happen to others? Well, let me just show you the video because I have to admit, I stayed late, it was like 6 o'clock, and I just went into a room, and I was all by myself, right? So nobody was in the room. And I just started recording myself, talking to no one. But I pretended that you were there. And so if you watch the video, you'll see me ask questions of you, and then wait for a second, and then be like, yes, that's exactly right, good response. And then I keep going. So the entire lecture is well worth watching, if nothing else, because you can tell I'm having a really good time. I think I'm very funny in the video, and so for that sake alone, I think you should all watch it, but also because it has such good material. I really covered the material very well, very thoroughly. Same material I'm going to cover today. So in other words, you can watch it today, go home, watch it again, and you'll feel even more confident. You'll say like, okay, yeah, now I really get it. So in fact, I'm really glad that I did record this because this material is really important material. It forms like the bedrock for what we do. So do I have volume? Oh, it'll play volume for you at your own computer. So anyway, please go online. The video is linked. If you go to, first of all, I sent you an email.
That link doesn't.
It doesn't work, yeah.
This link doesn't?
No, because you used the wrong one.
Oh, you're
Yeah.
kidding me. So then how did you watch it?
Well, I just went into YouTube and typed in your.
Yeah, exactly your name.
Yeah.
No,
Okay.
That's the creator site.
I used the wrong one. Well, that's a problem. So let me see that. I would have to go to, well, that explains a lot. Okay, so where's my, here's mat213. This is us, and so there's that video lecture. And so this would be the correct link, is what you're saying. Oh, I'm so sad. Well, in any case, folks, now you can go home tonight, pour yourself a nice tall glass of iced tea, and watch it after the fact. Hey there, Molly. So thank you for that feedback, Josh. Hey, folks, if you ever get like a weird error like that, like Rosa or Josh, please just email me to let me know so that I can post the correct one, because I want everyone to be able to watch it. Okay, well, I'll post that in a second.
That was just my computer.
Oh, yeah, I mean, you know, sometimes it is just your own computer, but sometimes it's, you know, the teacher's fault. That happens for sure. So next time, shoot me an email so that I can fix it for everybody. So I am going to fix it right now then. I'm going to go into our Canvas site and go to announcement. And I will go ahead and post a new announcement that says, watch this video. It's fantastic. And then here's the link right there. And now you'll all be able to watch it if you haven't already.
Okay.
Yeah, no, thank you. Okay. So then, Molly, what I was just saying is that I wasn't here on Thursday, but I recorded a video of myself doing a lesson, which I'm going to recap today. So again, I really recommend all of you are here, you're going to watch it today, but then go home and watch it again on the video. Kick back your feet, do some laundry or do some dishes, but listen to the video again, watch it again, because really what we're about to do today is really important that everything else is based on. And what else did I want to tell you? In addition to, oh, go ahead. Oh, I did, I got a haircut. I wanted to tell you 2 crazy stories. I mean, I'll tell you a joke as well, although I don't see a joke up there. So my 2 stories will count as a joke, because I already told you those. So first of all, yesterday, I'm leaving a math class here on campus. I'm going down the freeway, and then wham, someone rear ends me. I'm in a 5-car pileup. Okay, so fortunately, I'm okay, and the rear of my vehicle is the only thing that was damaged. The crazy part is, the person behind me, he got hit by somebody else, and so then he slammed into me, right? So it wasn't the guy who hit me's fault, it was the guy behind him. The person behind me was a student who was just in my class. Like, we were doing a class, we both left, got in our own cars, driving away the freeway, and then bam, he slammed into me. Totally, how does that happen? That's just so random. Okay, but then my funny story for you is, I woke up this morning and I wanted to wear this tie. I just thought it matched this shirt, I thought it was great. My wife says to me, why are you wearing a Christmas tie? I'm like, honey, this is not a Christmas tie, it's a Tigger tie, and he happens to be bouncing in the snow with presents, and so he's wearing a Santa hat. That doesn't make it a Christmas tie. She didn't agree. All right, so here we go, folks. Let's go ahead and get started. Everyone, we were finishing up section 2.2. And where are we, by the way? We're on January 29th. It says here, finish 2.3 and begin 2.4. We have a lot of duplication in the schedule right now, so we have plenty of time to catch up on everything. We'll finish 2.2 and 2.3 today, and then we have a few more class periods to finish all of 2.4 and 2.5, and then you have the test. Okay, I already adjusted the due dates on more, so that you only have to do, the only thing to do today was what? There's just 2.1. No, just 2.1, right? We didn't finish 2.2.
The due dates for 2.1 and 2.2 is separate.
Oh, well then I'll fix 2.2, because aren't we about to finish 2.2 right now? Yeah, so I'll extend that due date for all of you, okay? Okay. Did we finish 2.2? Oh, we are? So what, 2.3 is on continuity? I'm sorry. Yeah, we had a couple problems left on 2.2. So let's finish 2.2. So did we finish these 2 problems? I think we did.
Yeah, well, in the video.
Yeah, and just to clarify real quickly, so to evaluate the limit, we were just talking about this. They want to know what happens as x gets really, really close to 6. Well, if you actually plug in 6, that's a problem. If you plug in 6, you get 7 times 6 is 42 over 42 minus 42, which is 0. Then if you plug in 6, you get 36 minus 12 minus 24, which is 0. So you can't actually evaluate that function at 6. So instead, you'd have to factor the top, factor out the 7 to get x minus 6, factor the bottom to be x minus 6, x plus 4. That allows you to cancel out the problematic element in the bottom that was causing you to have 0 in the denominator. Right? Notice x minus 6 was the problem. Because if I plug 6 into 6 minus 6, that's 0. It wasn't the x plus 4 that was a problem. X plus 4 is fine. I could plug 6 into x plus 4, and that would just be 10. So the problematic binomial was the x minus 6. By factoring, you get to cancel it out, and then you're left with 7 over x plus 4, and now you can plug 6 into this expression, and you simply get 7 over 10. Yeah?
So how would you rearrange that to also that you could use the negative one?
Oh, you would not be able to. If you were trying to look at what happens at x approaches negative 4, there would be no way to cancel out the x plus 4 term. It would be what we would call a permanent discontinuity. Thank you, Josh, for the question. This is really interesting, folks. There's a lot of really interesting things in calculus, kind of philosophical. I want you to notice this function and what its characteristics are. So what was it? It was 7x minus 42 divided by what?
squared minus 2x minus.
So take a look at this function. First of all, notice that at x equals 6, what is there? A whole. Okay, so by factoring out the x minus 6 part, what was the function we ended up with? 7 over x plus 4?
Yeah.
I want you to look at what 7 over x plus 4 looks like. What does the graph look like? It's exactly the same function. The only difference is if you look at the blue function, where I took out the x minus 6, now is there a whole? No, the whole is gone. So this is really cool. So when you factor and cancel the problematic term, you fill in the hole. Isn't that weird? It's a little crazy. You fill in the hole. That's it, just that one hole. You fill it in. Okay, so that's what happened when you factored and canceled, you filled the hole. So here's my problematic function again. It still has the hole. But now look at what happens over at minus 4. Minus 4 is no mere hole. Minus 4 is an entire vertical asymptote. That's a much bigger problem. That is not a hole, that's an asymptote, where the function is going up to infinity up top and then down to infinity down below. So there is no way to repair this. This is not a mere hole that you can put one little point into and then it's all patched up. This is an asymptote. And so that asymptote discontinuity is permanent. Josh, does that answer your question? Yeah, so you could say that the x plus 4 term is permanently damaged, right? That ruins the function. An asymptote is irreparable. Okay, really nice. Okay, yes, Sarah?
So I'm going to evaluate the questions.
Yeah.
With this, like, for example, the 7x minus 42 over the equation. So when it's been evaluate the limit, the number like x to 6, that's the whole.
Right,
That's what makes it equal to 0, that's why I have to like factor it.
Yeah. Yep. Because you saw what just happened. The original function was red and it had a hole in it. By simplifying it, that was the blue function with no hole in it. And because there was no hole in it, you were able to actually plug 6 in there and actually get the value of the function.
For the bottom one.
What, this one?
Yeah.
Yeah, this one, you'll notice there's no denominator. And so you never divide by 0, and so this function has no holes and no asymptotes. So in other words, this function is purely continuous. This function is absolutely continuous, and therefore you can just plug 3 into it and you can know what the value is. The only reason that we have such thing as this whole discontinuity and factoring and canceling is to deal with holes and asymptotes. This function has no holes and no asymptotes. It's perfectly continuous. So you can just plug 3 into it and you're fine. Okay, Sarah, great question, Josh.
So going back to number 6, factoring. So instead of x minus 6 and x plus 4 could be x plus 6 minus 4, or would that just be
It would be a different equation. Like, are you asking what if it had been 7x plus 4 over x minus 6x plus 4?
No, if only the denominator, instead of factoring it as x minus 6 over x minus 6 times x plus 4, could it be x plus 6 times x plus minus 4?
Oh, like what if it had been this?
Yes.
Well, if it had been that, that would have been a different function, and there would have been a hole there. It would have been 2 asymptotes. So, folks, this is really interesting. Okay, this is what's interesting about calculus. So, if you change that formula, as Joshua just suggested, to be instead x minus 6, no, x plus 6, and x minus 4. So, that in other words, Joshua, that those terms aren't going to cancel, right? That's what you want to know. Yeah, you'll notice now that this does not have a hole at 4. It has a whole other asymptote. So now, folks, if you look, you've got an irreparably damaged asymptote at -6, and you have an irreparably damaged asymptote at 4. Those are both asymptotes. You cannot fill in asymptotes. You can only fill in holes. So there is no way to evaluate this limit. In fact, Joshua, what you'd say about this limit is that it does not exist. Because notice, folks, if you approach 4 from the right and you approach 4 from the left, are my fingers going to touch? No, in fact, my fingers are going to be infinitely far apart, which is going to hurt. right? So no, this limit does not even exist. It was only when the limit was a hole, so again, now let's look again what the hole looked like. Only with a hole were my fingers even going to touch, right? So here, my fingers are touching, therefore it is continuous. There just was a hole there. Does that answer your question, guys? Okay. These were great questions, folks. So now let's see the interesting one. We've seen now how to factor. There we go. We've seen how to factor, but what about these expressions? This requires an entirely different type of mathematics to simplify. Now you might ask, okay, so there's a square root, and what exactly is going on in this function? Like, why is it discontinuous? Is it discontinuous because there's a hole, or because there's an asymptote? So let's look. If I go ahead and type in this function, we've got square root of x minus 12 all over x minus 144. And we're asking what happens as you approach 144. So let's go on over there to 144. So there's 144. And what's happening at 144? There's a hole. So that means that this is reparable. You can repair this by simplifying and canceling. So the question is, how do we simplify and cancel? So there is no way to factor that square root term. And instead, what you're going to do is multiply by the conjugate. So first, just to review this word conjugate. A conjugate simply means a pair. And so a conjugate would be like, you all remember your difference of squares formula, x squared minus 25. You can factor that into x plus 5, x minus 5. So that's just a basic factoring technique. These two things are called conjugates because they're both x and 5, but one of them is plus and one of them is minus. So we say something, if we're talking about a plus b, the conjugate of a plus b is a minus b. They're conjugates because it's the same numbers, but one's plus, one's minus. We call this a conjugate. Conjugate. So what we're going to do is multiply by the conjugate of the square root item. So everybody, let's all start this together. If you take your root x minus 12 over x minus 144, what we're going to do is multiply by the fraction of the conjugate, top and bottom. So instead of root x minus 12, we're going to put root x plus 12 over root x plus 12. This is called multiplying by the conjugate on top and bottom. Now, first of all, why am I even allowed to multiply by this thing? What is this thing equal to? It's just equal to 1. Because anything over itself is equal to 1. 5 over 5, x over x, 20 over 20. Anything over itself is equal to 1. So I'm taking this expression and I'm multiplying it by 1. And if you multiply by 1, are you changing anything? No, you're allowed to multiply by 1. Okay, so we multiply by 1. And by the way, why are we even doing work? Can't I just plug 144 into this? Why not? What happens if I plug 144 into that? Yeah, the root of 144 minus 12 over 144 minus 144. That's 12 minus 12 over 0, which is 0 over 0. So no, you can't just plug in 144. That's why you have to do work. Okay, so let's try this method. We're multiplying top and bottom by the conjugate of the numerator. So the only work you actually have to do is FOIL the numerator. So let's FOIL the numerator. First, what's root x times root x? Yeah, root x squared. Outer, root x times positive 12, that's plus 12 root x. Inner, negative 12 times root x, that's minus 12 times root x. Which, by the way, something really exciting just happened. What is it? Yeah, those are going to cancel. And then you have last, negative 12 times positive 12 is minus 144. And that's all over this nasty looking thing that we're not going to touch or FOIL. X minus 144 times root x plus 12. Notice that you do not have to FOIL the denominator. Not only is it not necessary, it would be unhelpful. Okay, but now what do we have in the top? The 12 root x's cancel out. What's root x squared? They're just x, because when you square a square root, that cancels out as well. So lots of cancellations, and now we're left with, on top, just x minus 144. Lucky us. we have another x minus 144 on bottom. And keep in mind, the x minus 144 was the offending term in the first place. We wanted to be able to cancel the x minus 144 because that is the term that was causing the 0 in the denominator. So from get-go, our goal was to eliminate or cancel the x minus 144 in the denominator because it was causing the problem of the 0 that came out in the denominator. And so by doing this trick of multiplying by the conjugate top and bottom, we ended up with being able to cancel the offensive term, which is the x minus 144. So what are we left with on bottom? Root x plus 12. What are we left with on top? We have 1. So what I want you all to notice, and I think I said this last time, calculus is really just a lot of algebra with a lot of manipulation and simplification. And what we just saw here was a lot of algebra with a lot of cancellation and simplification. So now what happens when we plug in 144? Now we get 1 over 12 plus 12, which is just 124. So let's see, is that really what the graph showed? Is our function approaching 1 over 24? By the way, what is the value of 1 over 24? Did you know that Google is a calculator? If you just Google a math problem, 1 divided by 24, they'll tell you the answer. So it should be approaching 0.041666. Now let's take a look. Am I approaching 0.04166666? Yeah. I mean, there's a hole there. But if not for the hole, it would be approaching 0.04166666. Now, furthermore, notice, what if I replace the function I started with the new function, 1 over the square root of x plus 12? What do you notice about our two functions? They're the same function, except what do you notice about the black function? Is there a hole? No, there's no more hole. We filled it. And therefore, now the function is continuous. Now you can draw it without picking up your pencil. All right? So what was this technique called? It was called multiply top and bottom by the conjugate. So let's try that again. We'll try that on number 9. We have this expression. If I graph it, there would be a hole. And we're trying to approach 0. And obviously, right now, if I plug 0 in for x, my denominator would be 0. And my numerator, 6 times 0 is 0. 0 plus 16 is 16. The square root of 16 is 4. And 4 minus 4 is 0. So this is indeed problematic. You can't just plug in 0. So we're going to manipulate this expression. And what are we ultimately trying to cancel out? The offensive term in the denominator. In this case, up here, the offending term was x minus 144. But here, the offending term is just x. We want to do some algebraic manipulations so that in the end, we're going to end up with an x on top and an x on bottom, and then we can cancel them out. So let's try it. We have this numerator, which is root 6x plus 16 minus 4 all over x. And what I want you all to notice here, this term, root 6x plus 16 minus 4, this is the thing that we're actually conjugating. So the conjugate of root something minus 4 would be root something plus 4. So those are conjugates, root something minus 4 and root something plus 4. So when we write down the conjugate right now, I'm going to write root something plus 4, root something plus 4. Whatever's inside that root, it just comes along. We're not conjugating the 6x plus 16. Some students think, oh, well, we have to change 6x plus 16 into 6x minus 16. No. This is just a root minus 4, so we're going to multiply by the conjugate root plus 4. So the 6x plus 16 stays the way it is. We're conjugating the expression as a whole. Root minus 4, root plus 4. Joshua.
How would you conjugate an expression with more than 2 terms?
You wouldn't. This only works with 2 terms. Yeah, good question. All right, folks, so let's try it. Again, you do not have to FOIL the denominator. In fact, if you want to make yourself feel good, just go ahead and write down the denominator and sit back with a satisfied, hey, I'm already done with the denominator. All right? Because the denominator just stays. Whereas the numerator now, we have a bit of work to do. We have to FOIL that whole expression. It's not going to be too bad though, because I bet all of you can now predict what's going to happen to the middle two terms when we FOIL. Then they're going to cancel out. And in fact, that's the whole point of conjugates. That if you multiply two conjugates, a plus b and a minus b, the whole point is that when you FOIL conjugates, you cancel the two middle terms. So this would be first a squared, outer minus ab, inner plus ab, last minus b squared. The whole point of multiplying conjugates is that the middle terms always cancel. That's why you have this structure of a plus b and then a minus b. Okay, so let's do it FOIL. First, we've got this root squared. And then we have outer, so that's the root times 4, so that's plus 4 times the root. And then inner, negative 4 times the root. And then last, negative 4 times positive 4 is minus 16. Now you notice I was being a little cheeky there. I didn't even bother writing down what was in the root. That's a little lazy on my half. But at the same time, it's also just an acknowledgement that there's not even a need to write it down because those terms are canceling out anyway. And what happens with this root? The root being squared? Yeah, that root cancels out, and so we're left with just 6x plus 16 minus 16. 6x plus 16 minus 16. This is really exciting. Root 6x plus 16 plus 4. And so what happens now in the numerator? Yeah, those 16s cancel out, and once those 16s are gone, now you have a 6x over x times this root expression, 6x plus 16 plus 4. And now what happens to those two x's? They cancel out as well. Because you have an x on top, you have an x on bottom. If you want to wrap everything in parentheses to see why that works, remember, you're only allowed to cancel things top and bottom when everything is a product. You've got this times this, and then this times this. When everything on top and bottom is a product, you're allowed to cancel anything that you see on top and bottom. And so we're left with, finally, after this massive algebraic manipulation, 6x plus 16 plus 4. So now what did all that work do for us? Now we can plug 0 into this expression. Now we can actually plug 0 into this, and we end up with 6 over 6 times 0 is 0, 0 plus 16 is 16, the square root of 16 is 4, 4 plus 4 is 8. And we end up with this very simple 3/4 or 0.75. Just to visually confirm it, because I'd like to really solidify this idea that when you go home every day and you're doing homework and such, you should really be typing these things into Desmos and verifying every problem that you do. So you can just type in that divided by x. Here's my graph. Let me zoom out a little bit because we're approaching 0. Here we go. So here's my graph, kind of a strange looking graph that starts right here, and then it just kind of slopes downward and heads up that way as an asymptote towards infinity. And so what happens as x approaches 0? That's what we're curious about. And, oh, just like we suspected, there's a hole. Now, by doing all of that algebraic manipulation, we ended up with 6 over square root 6x plus 16 plus 4. What do you notice about the two graphs? They're identical, right? So all that algebraic manipulation provides us with two graphs that are identical in every respect, except for the fact that the hole was filled. And look at the value. If you plug in 0, you get 0.75, which is what you expected. Now, folks, you might look at all this, okay? Everything that we just did. We just did some real heavy lifting. Really, I mean, aren't you impressed by the algebra? I mean, this is some good looking algebra. This would lose most people, right? Because I mean, I've got all these steps, all these cancellations. And so there's a couple of themes that I want us to talk about in this class. First of all, so theme 1, calculus, is tons of algebraic manipulation and simplification. So it's kind of like all the algebra you ever learned in your whole life. This is why you learned it, so that you could actually come in here. Did I write it? Okay, good enough. So you can actually do calculus, because calculus is just tons of algebraic manipulation and simplification. We're going to review rules that you learned years ago. You're like, oh my gosh, that's why we learned that rule? Like even just right now, conjugation. Conjugation allowed us to manipulate a function with a hole into a function that doesn't have a hole. Right? How would you have ever predicted that years ago when you learned this phrase conjugate, that like the difference of squares rule, that you would actually do something a little more significant with it. So that's one thing. Second, and this is a big one, because I care about you and the emotional experience that you have in this class. Sometimes you'll be going through some work and you'll start to get a little sad inside. Like, oh my gosh, this is so many steps and so much work and feeling sad. Here's the good news. In most of the problems that we do, it gets worse before it gets better. All right, so that's the good news. It's going to get bad. Guys, it's going to get bad. You're going to find yourself in some low spaces. But before you get to the end of the problem, it gets better. And you're like, wow, that really simplified really nicely. Like, you had to trudge through all this mud and gut to get there, but then you come out on the other side and you're like, oh my gosh, seriously, the answer is 6/8? I mean, look at all this nastiness and you're like, oh, it's 3/4. Right? I mean, that's surprisingly elegant and simple. So it gets worse before it gets better. And then what was the last thing I was going to say? I forget. I'll remember it as we go. Okay, so what did we really just learn right here? Sure, we did some algebraic manipulation, but we also experienced the theme of the course, that calculus is tons and tons of algebra. You can expect it to get terrible, but then it simplifies really elegantly at the end. And you're like, wow, calculus is very elegant. Okay, ready to keep going? The last part of that previous chapter was talking about the actual definition of a continuous function. So let's talk about the actual definition of a continuous function. There are 3 parts to the definition. So let's fill, do you have that 3 lines up at the top? Yeah, you do, okay. So let's fill that in together. So what are the 3 criteria for a continuity? First, let's take a look at this function. Of course, my board is right on the dot. There we go. Yeah, so let's look at this point right here. We're going to look at that point right there. Now, first of all, is this line continuous? Can I draw it without picking up my pencil? Yeah, the whole thing's continuous. What we want to be able to say is that the entire function is continuous. But in order to say that the entire function is continuous, what you really say is any point that you choose is continuous right there. And if I choose this point, I can show you it's continuous right there. And if I choose this point, I'll show you it's continuous right there. And the whole proof that an entire function is continuous rests on being able to say, hey, you choose any point you want. You come up here and point to any point on this line, and I can tell you that that point right there is continuous. And if for any point you choose, I can show you that it's continuous, then you conclude that the entire thing is continuous. So let's pretend that I just said that. I said, hey, anybody you want, come on up here and point at a point on the graph, and that was the point you chose. Okay? And I'm going to show you that this point right here is continuous. So what's the definition? First of all, the first idea is that the limit exists. And remember, for the limit to exist, that means the right-hand limit and the left-hand limit have to be approaching the same thing, i.e. your fingers are touched. So that's the first criteria, is that for a function to be continuous at a point, your fingers have to be approaching each other. You know, not like a jump and not like an asymptote. They have to be approaching to each other. So that's the first criteria that limit exists. Second criteria is that when you are talking about this value, you know, you chose right here, which was x equals 2. Does everyone see that that's x equals 2 right there? It's not labeled. Here. 1, 2, 4, 5. Yeah, so when we're talking about x equals 2, you also have to be able to say that there is actually a coordinate there. There is a coordinate, meaning I can plug 2 into the function, right? Like if my function was 1 over x minus 2, I'd be in trouble. I can't plug 2 into that. 2 minus 2 is 0, 1 divided by 0 is 1. But what I'm saying is that there is actually a coordinate somewhere at x equals 2, namely where the fingers are touching. So the key is that for the input value of 2, there must be an output value. And that's all we're really saying. For the second criteria is you're just saying, I can plug the number in and my calculator will give me an answer. My calculator will not say undefined. So that criteria is there is actually a point somewhere. And the third criteria is that your fingers are actually touching at the point that's actually there. So this criteria kind of brings both criteria together. That your fingers have to be approaching each other. There's got to be a point somewhere. And your fingers are approaching each other at the point that you said was there. Okay, so there, I just said it all, but now let's write it down. So your three criteria for a function to be continuous at a point. So everyone say, consider x equals a. Okay, so we're just choosing some value. I'm going to call this point A. Everybody, you can also call it point A. So choose some point A, and we're going to say, hey, I bet that function is continuous right there. So the first thing we'd say is that the limit as x approaches A of that function exists. So remember what I said was any one of you is allowed to come up here and choose any point on this line you wish. So we chose point A, x value, x equal to A. And the first criteria is that that limit has to exist. And remember, for a limit to exist, that means the right-hand limit and the left-hand limit are equal to each other. So what we're saying then is your fingers touch. Right. That's criteria one. For a function to be continuous at a particular point, first of all, your fingers have to be approaching that point. Second of all, f of a actually has to exist. That whatever point you just chose, you have to be able to plug it into the function and it will actually calculate an answer. I.e. not a calculator error. It can't say calculator error. It has to actually give you a numerical answer. And so we say there's a point right there. Another thing you can say is you can plug A into f of x and not get a calculator error. All right, so that's the second criterion. The third criterion really just merges those two criteria together. Okay, so the third criteria is just stating that where your fingers are touching is at the point that you calculated when you plugged in A. So now we just go ahead and say that the limit as x approaches A of f of x is equal to the point that you found by plugging A into the function. Meaning the fingers touch at that point. So those are your three criteria. Let's do those three conditions right here for this function. This function just happens to be 2x. Nice and simple function. That graph that you're all looking at on your own paper is just f of x is equal to 2x. So what's the first criteria? The first criteria is that as we approach, oh, and by the way, let's choose x equals 2. So look at x equals 2. So we're going to try to say that the function is continuous at the x value of 2. So the first criteria says, what is the limit as x approaches 2 of f of x? So what are our fingers approaching? What y value are our fingers approaching? Yeah, it's approaching 4, right? That's 1, 2, 3, 4. So sure enough, our fingers are approaching the value of 4. So yes, the limit does exist because from the left and from the right, our fingers are approaching each other, and they happen to be approaching 4. Criteria 2 states that at that particular value that we're looking at, if I plug 2 into the function, what will I get? If I plug 2 into this function, 2 times 2 is also 4. And so criteria 3 is just really showing that those two things actually equal each other. And so you would say, yes, the limit as x approaches 2 of f of x really is equal to f of 2. And you put a big smiley face. Because that means that it is continuous. Now all I just did was show you that this function is continuous at x equals 2. Like for sure, right there, it's continuous. I can draw that part of the graph without lifting up my pencil. Now, that really teeny little portion right there. I can now sit back and say, whew, I can draw that part without lifting my pencil because there's no hole And then you'd say, hey, the whole thing is continuous, because if you choose any other value besides x equals 2, like if you just happen to choose x equals -3, what can we do? We do the whole process all over again. I could choose the value x is -3. I can repeat these 3 steps and show you that these 3 tests are also passed by the value of x equals -3. Okay, that's it. These are the 3 rules that mathematicians that came up with to say that a function is continuous. I acknowledge that these 3 rules might seem arbitrary or maybe perhaps overly specific. Because after all, don't we all just want to say that a function is continuous? You can draw without picking up your pencil? I mean, that's the idea that we're trying to get at. And yet, to say it mathematically, they had to come up with these 3 different rules. And then these 3 rules are equivalent to saying you can draw without picking up your pencil. So that's it. What questions would you like to ask about these 3 rules? Or perhaps we should do some examples and then you can ask more questions. Let's take a look at our examples. We're going to talk about these next couple of functions and say why they're not continuous. Here we go. All right, so look at the graph in number 10. You can all just tell me right now, is that graph continuous? No, of course not, because you couldn't draw it without lifting up your pencil, right? There's this huge jump. So it's one thing to say, no, it's not continuous, but it's an entire other thing to actually give a mathematically rigorous reason why it's not continuous. So let's go through the 3 rules. Now, notice, folks, these 3 rules are out of order. This was the first rule we talked about, this was the second rule we talked about, and that's the third rule we talked about. I apologize for that. Let's go in order that we did it. Okay, so let's look at rule number 1 first. Does the limit exist at the point x equals -1? Let's read the instructions. The graph below is for the function. Which rule for continuity is violated at x equals -1? So we're looking at the x value of -1. And so the first rule was, does the limit exist? I.e., do your fingers touch? So at x equals -1, do your fingers touch? No. So we would say rule number 1, violated. That sounds terrible. Violated. It's the word that they use for the program. All right. How about rule number 2? Is there actually a coordinate defined at -1? If I plug -1 into the function, will it actually give me a coordinate? Yeah, it actually will. It'll give me the coordinate -1 and 2. Meaning, if I take my function and I plug in -1 and I type it into my calculator, it'll actually give me the answer 2. It won't give me a calculator error. It won't say divide by 0 error. It'll actually tell me the answer is 2. So f of a is defined. Yes. Rule number 3 is the limit where your fingers were touching the same as the value that you got for the coordinate? And the answer is no, because our fingers don't even touch. You know, rule number 3 can't possibly be true if one of these rules is violated. Pretty much if either the first or second rule is violated, 3 is absolutely violated. So the limit of where your fingers touch, are they touching at that coordinate that you found? No, because your fingers aren't even touching. So now we can say for sure that this function is not continuous at x equals -1, and we can pinpoint why it's not continuous because the fingers aren't touching. What's funny? All right, now how about the second one? Does this graph look continuous? No, I mean, it's better than that one. This one's better, but now we have a hole. Right? So again, we can't draw this without picking up our fingers, picking up our pen. So we already know it's not continuous, but now let's say exactly why. This was rule number 1, rule number 2, and rule number 3 in the original order that we looked at. So rule number 1, does the limit exist? From the right and from the left, are our fingers about to touch?
Yes.
Yeah. Yes, the fingers are about to touch. So that's okay. That's one aspect of continuity. Or rule number 2, is there a coordinate at x equals 2? No, there is no coordinate. Anywhere. Look up, look down, there's no coordinate. So for this particular function, if I plugged in 2, what does that mean happened? You probably got some sort of 0 divided by 0 calculator error, because there's a hole. What's that? Yes, so that one's violated. So that rule was not true. And therefore, rule number 3 is is definitely violated as well, because even though your fingers are touching, there was no point. So that's enough. Okay. Yeah, so that's the mathematically rigorous definition for continuity. Intuitively, we just mean that you can draw it without picking up a pencil, but mathematically, you need those 3 rules. Well, that's perfect timing for my phone to go off, because now we have a 10-minute break, and then we're going to come back and we're going to start looking at the definition of the derivative. So today, we actually get to start deriving the formula for the derivative. So remember, our ultimate goal is you take some sort of function, like f of x equals x squared, which is a parabola, and you want to come up with a function called f prime of x, that for any x value you plug in, it's going to tell you the slope. That's really exciting. The function tells you the height, how high you are. The derivative tells you the slope at that point. So that's what we get to start doing today, is actually deriving the formula for the derivative. Okay, the time is 11:51, so I'll be back at 12:01. Yeah, I will, as a matter of fact. Yeah, I think I have it in here. I do have it.
And these are the note packets we turn in.
Yeah, these are no packets we turn it in. There you go.
I have a question regarding my homework.
Okay. What is that question? Okay.
So for these two, wrong.
It could be that you're not keeping enough decimals, because it wants 4 decimals of accuracy. And so since you're already rounding here, since you're already rounded that number, when you divide by that, it's not going to be accurate. So I think that what you just need is more decimals of accuracy. And since the program wants 4 decimals of accuracy in the final answer, that means that each value that you keep in here, I better have like 8 decimals of accuracy. So that by the time you're done subtracting and then dividing, you have 4 accurate decimals of accuracy at the very end. Does that make sense? Does it? Yeah, I think that's it.
Then also, I was really confused on number 4.
Okay.
Are you able to go out to the after hours or?
Yeah, you come up to office hours or?
I'll do it.
Sweet. 2.1, you say?
Yeah. We'll do it. I'll go to your after hours.
Okay, but I'm happy to give you some insight right now, because you know it's always nice to have your question answered as soon as possible. So 2.1, number what? Number 4. Let me see your work for it. Yeah, I'll just check your work.
Why erase it? I was like.
Well, in the future, never erase, because erasing, you could have like everything right except one teeny little thing. So the problem was -5b, -3. Okay, perfect. This is great. So far, what you got plugged in here is exactly right. 90 squared minus 3. And then minus whatever all that is. So let's see what that is. See, you probably had it all right, Lisa. Don't erase next time. So go ahead and write down 90 squared minus 3 minus 222. Because that's what it is. So 90 squared minus 3 minus 2. All of you were here at the start of class and got all nervous. So, no, I don't want to see
No, I'm fine.
Okay, now, what's
nervous.
Oh, I see. Equals. Negative 3 minus 222 is 90 squared minus 225, right? Well, that's important. Okay, so this is probably where we were last time, right? Okay, so now you can factor 9 out of 5. So factor 9 out of 225. So just take 225 and 5 9. So it's 25. So now you have 9 in the numerator, you have 9 outside of it. B squared minus 25. All over B minus 5. And now notice, B squared minus 25, you can factor that using difference of squares. In fact, I even did that example on the board a second ago. So B squared minus 25 is actually there we go. So you're almost done. There you go. Now, in the future, is it? Never erase anything for the rest of your life. You can cross things out if you want to, but don't erase. Yes, just yes. 9 times B plus 5. There you go. Yep. And that means that whatever the value now that you plug in for B.
I was different.
Okay. Yeah, you can factor out the 9.
Yeah, I was like,
and then
what do I do with the 9? What do I do with it?
good question.
What do you want to put back?
Hmm?
What do I want to put back?
I wrote it on the board. Oh, I erased it. Hold on. All right, folks, let's keep going. Now, this is the really exciting part. What we're about to write down and draw together is so very important, we're going to write it down many times. And the important thing is for you to go home and try it a couple times on your own, right? So what we're going to do is begin by doing a specific example of actually deriving a formula for the derivative. So let's all start by considering this simple function x squared. So let's all go ahead and draw it. We have an x and y axis. We know it's a parabola, so we start here, and then the parabola shoots off like that, and that's my function f of x equals x squared. Right? It's just a parabola. You can draw the left-hand side if you like. So we have this parabola. And what we'd like to do is find the slope at any given point. So for instance, let's just go ahead and say that I want to find the slope right here, right there. I want to find the slope on the graph right there. So I'm going to draw a little tangent line to denote what that slope would actually be, right? It's a tangent slope. It's a slope at a single point. I'd like to know what that slope is. And what point are we going to call this? We're going to call this the point x. Not to be confused with the x-axis. I'm just saying, let it be any given point in the world, right? I'm just arbitrarily choosing some point. So what we know is that there is no formula for the slope at one point. There's only a formula for the slope at 2 points. And so here's the key part. What we're going to do now is we're going to move to the right some arbitrary amount h. We're just going to move h units to the right and find that point. And now we're going to call it what? What point is h units to the right of x? X plus h. So now we have that point. So those are the 2 points that we're looking at. And we're going to go straight up on our graph. One more, there we go. And let's go straight up and find that coordinate. So we have 2 coordinates now. We have the original coordinate x that we're interested in. Okay, this is the one we want. We want to find the slope of the parabola right there. And this is the point that we just arbitrarily chose to the right. So x plus h is an arbitrary point to the right. And so what we'd like to do is find the secant slope between those 2 points. Because we do have a formula for secant slope. The formula for secant slope, so I'm going to go ahead and find the secant slope between those 2 points. Because we can actually calculate that. So in order to use m equals y2 minus y1 over x2 minus x1, we need to actually figure out what those coordinates are. So what are those coordinates? Well, the first coordinate, the input is x. How do you calculate the y value? What's the expression for any y value? How do you know the height of a coordinate? F of x. Yeah, your function is always telling you how high the coordinate is. So what we're going to go ahead and say then, if this x coordinate is x, the y value is just f of x. That's going to tell us the y value of that coordinate right there. And therefore, this coordinate right here is x comma f of x. Does everyone agree with that part right there? Now we're saying that coordinate in space is the coordinate x comma f of x. Keep in mind, we just arbitrarily chose some point x that we're interested in. We want to know the slope right there, the tangent slope. And so we need to know the value of the coordinate. Well, the y value is always just plug that value into the function, and that's the y value. So this coordinate is x comma f of x. Likewise, now, what's the y value of this coordinate up here? The x value is x plus h, so what would the y value be? F of x plus h. Yeah, now that might feel a little awkward right there, writing down f of x plus h, but just remember, the fact is, for any given function, let's just say that I made it simple, like the number 3. How do I find the y value of 3? I would just plug 3 into the function. All right, so does everyone agree that this coordinate is also 3 comma f of 3? All right, just using a simple number, this is what we're talking about. So no matter what the input is, your y value is just plugging that number into the function, that'll give your y value. Okay, so we're ready to go here. So this coordinate is x plus h, comma, f of x plus h. So as of this moment, we can now calculate the secant slope between these two coordinates. So we're going to go ahead and call this x1, y1. We'll call this x2, y2. And now we can plug that information into our normal slope formula. Remember, just plugging this into our normal slope formula. So what would our slope formula be? The y2 is what? Yeah, f of x plus h. And then we're subtracting y1, which is just f of x. And then we're going to do x2, which is x plus h, minus x1, which is x. We can simplify this a little bit. What can we simplify? The numerator or the denominator? What can we cancel in the denominator? Yeah, we've got an x and a negative x. So we can get rid of that. And so now what we have is f of x plus h minus f of x all over h. Okay, now what you just did right here, that's very important. Go ahead and label this. This is the secant slope between 2 points, right? Which 2 points? Between x equals, well, between x and x plus h. Right? That's what we just calculated here is the formula for the secant slope between the point we're interested in and a point arbitrarily far to the right. That's what we just calculated. That formula right there, f of x plus h minus f of x over h, that is the formula for the secant slope between these 2 points. Now, again, what are we interested in? We're interested in the tangent slope, the blue line. What we want to know is the tangent slope at 1 point. We're not actually interested in the secant slope at 2 points. We want the tangent slope at 1 point. So now what could we do? We could start sliding this point closer and closer and closer and closer together. And if we start taking this point and we slide it closer and closer and closer and closer and even closer, eventually I want you to imagine that if I slide this point infinitely close, I would have 2 points that are infinitely close together, which basically means they're right on top of each other. That effectively makes them 1 point. And my secant slope would be calculating the slope between them, and it would be equal to the tangent slope that we're interested in. And that's the philosophy behind this. So how does that feel? Do you agree that if I take this point that was arbitrarily to the right, just h units to the right, if I slide that point infinitely close, then would you agree that the secant slope between 2 points that are infinitely close would be equal to the tangent slope at the original point? Because that's essentially what I'm asking you to all to agree to. So if I bring this point infinitely close, the secant slope between 2 points infinitely close is equal to the tangent slope at one of those points. That's what we're saying. It wouldn't even be a bad idea to write that down. The whole basis for this is the secant slope between 2 points that are infinitely close is equal to the tangent slope What's the philosophy there? Does it make sense? Okay. Okay, so then how do I slide this point infinitely close? How far away, how far to the right is this point? It's h units to the right. And if I want to slide it infinitely close, what would I have to do to h? I'd have to make h really, really small. How small? Infinitely small. And how do I say that? We take the limit as h approaches 0 of the expression f of x plus h minus f of x all over h. If I was able to make h infinitely small, okay? Infinitely small, but not 0. Infinitely small, that's what a limit even means. We're getting really, really, really close to 0. Then I would make these 2 points infinitely close, and this formula would tell me the tangent slope. So, on the one hand now, if I take this limit, this is going to equal the tangent slope. And therefore, this whole expression here, this expression right here, is equal to the derivative formula that we're interested in. So this is the process that we would do. By the way, notice, can I just plug 0 in for h right now? What would happen? I'm just going to do it over here. What if I did plug 0 in for h? I'd have f of x plus 0 minus f of x all over 0. And then x plus 0 is just x. I'd have f of x minus f of x all over 0, which is 0 over 0. And that's a problem, right? This is why I created all the tools of limits in the first place, so that we would be able to deal with this situation. Because right now, if you just plug in 0, you would have nothing. It would be indeterminate error, calculator error. So what we need to do then is we're going to do some algebraic manipulation to this to cancel out the offending term in the denominator. The offending term in the denominator is h. So once we actually do this process with a real function, we're going to do all sorts of algebraic manipulation, which is what we were just doing, and it will cancel the h from the bottom, and then we'll actually be able to calculate the slope. Okay? So this whole thing right here is the definition of the derivative. So this is what was invented in the 1600s by Newton and Leibniz. All right, so this is the deal right here. And I hope that gives you a sense of perspective. Like, this whole formula here is actually just, what is this formula really? It's just a slope formula. You know, we hold these people in such high regard, Newton, Leibniz, all these mathematicians and scientists, but what did they really just do? The slope formula. Okay, that's not really like mind-blowing. Really, I'm not trying to take away from what they did, but I'm just trying to bring calculus back into the realm of the normal. Like, calculus is not this mind-blowing thing. It's just the slope formula, written slightly differently. All we did was just choose 2 points and calculate the slope, and then bring the 2 points infinitely close together. That was the genius. To say, let's bring those 2 points infinitely close. That was the good idea. Otherwise, slope, I mean, that's just a slope formula. People have a slope formula for thousands of years. No big deal. Okay, everyone ready to try it? Okay, so I'm gonna, yes?
So that is derivative formula.
That's the derivative formula. And now we're gonna go ahead and do it now. So we just derived the derivative formula. Now we're ready to go ahead and try it with the function that we chose, f of x equals x squared. Oh, I changed the screen. Okay, so hopefully you still have room on here. Oh, that just took up the whole space, didn't it? Okay, well, silly me. You need a little more space. What's the next problem? That's going to take a lot of space. You might want to go somewhere else, have a sheet of white paper or something, or you can just squeeze it on there. So let's try it. What we're going to do is write down the definition again. So f prime of x, by definition, is the limit as h approaches 0 of f of x plus h minus f of x all over h. So first of all, that's just the definition. And now we're going to proceed to manipulate. It's going to get worse before it gets better. But then when we get to the end, it's going to be so easy. It's going to be this nice, simple, elegant expression. Now, first of all, that limit as h approaches 0, technically, we should write it in front of every single equals that we do. But, oh my goodness, that would take up a lot of extra time. So let's just all remember, we're about to do a lot of algebraic manipulation, and when we finally get down to the very last part, we're going to write limit as h approaches 0 in front of it again. Okay? Okay, so f. What is our f again? It's just x squared, right? F of x equals x squared. So if I write that empty, f of something equals something squared, I can put anything I want into it, like 4, and then it would just be 4 squared. But what I want to put into it is, what are we going to plug into it? X plus h. So what is f of x plus h? Just x plus h squared. So let's go ahead and start by writing that down. We have x plus h squared. And f of x, well, that's just the original function. That part, you're always just going to write down whatever the original function is. So that's just x squared all over h. So keep in mind, folks, this was the general formula for all derivatives. Okay, now this, we applied it to a parabola. All right, so that's the very first thing. You just write down the formula, and then you apply it to whatever function you're talking about. Okay, so now what? What's x plus h squared? I'm going to do a bunch of scratch work over here, because we don't want to mess up our nice little derivation of scratch work. So what is x plus h quantity squared? Well, let's write it out first. So it's x plus h times x plus h, right? So we actually have to FOIL. So FOIL, so first, that's x squared. Outer, that's hx. Plus inner, that's another hx. And then last, that's h squared. So we have x squared plus hx plus hx plus h squared. What can we do? We can combine like terms. So that's really 1hx plus 1hx. That makes 2hx's in the middle. And that's what we have. So that whole expression, x plus h quantity squared, is really x squared plus 2hx plus h squared minus x squared all over. Okay, so in keeping with our theme, when you do calculus, you do lots of algebra. It gets worse, but then it gets better. So watch, it's about to start getting better. So what can we cancel first of all? Yeah, we can get rid of the x squared term, right? So that's gone. And what are we left with? We have 2hx plus h squared all over h. But yeah, now what can we do? Now we can factor out the h as well. So we factor out the h, and that leaves us with 2x plus h all over h. Right, now the h's cancel. Now remember, this was our big goal. The big goal was to cancel the offending term in the denominator. That h is the offending term in the denominator because the h, of course, we want to take the limit as h approaches 0. If we plug 0 in for h, we get a 0 in the denominator. So our whole goal from the beginning was to cancel the h out of the denominator because that's what was causing us to divide by 0 and get an error message. And so what do we have left? 2x plus h. It gets better. It gets even better than that. Remember, the actual formula was f prime of x equals the limit as h approaches 0 of 2x plus h. So I finally brought back my limit. Technically, we should be writing limit, 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 limit in front of all of those expressions. But now that we're all done, we finished simplifying, now we want to take the limit as h approaches 0. Can I go ahead and just plug 0 in for h now? Yeah, I sure can. And so, plugging 0 in for h, that's just 2x plus 0, that's 2x. And that's it. That is the derivative. And so what we can say now is kind of summarize that on our graph of a parabola, the function is x squared. That tells you the height. But the derivative is simply 2x, and that tells you the slope. So we'll just consider a couple points on this parabola to show you how cool, how wonderful this is, what we just found. So let's consider the value x equals 0. Right? So x equals 0. I'm going to make a table of values here. So here's my x. Here's my f of x, which is my height. And then here's my f prime of x, which is my slope. So what if I plug in 0 for x? First of all, what's the height when x is 0? How high up am I? 0, right? And sure enough, 0 squared is 0. So the height formula worked. And what's the slope at the bottom? The slope at the very bottom is a horizontal line, so that slope is also 0. And if I plug 0 into the formula 2 times 0, I get 0. So far, so good. The height formula really did tell me the height, and the slope formula really did tell me the slope. So now let's go over here a little bit. Choose a point at x equals 1. So if I choose x equals 1, first of all, what's the height? I would plug 1 into my height formula, 1 squared equals 1. So that is the height of that point right there. And if I plug 1 into the slope formula, 2 times 1 is 2, that tells me the slope right there is up to right 1. So the slope right there is up to right 1. Likewise, what if I choose a point over here to the left at -1? Well, we know that the points should have the same height because the parabola is symmetric. So if I plug in -1, the height would be -1 squared, which is also 1. So sure enough, the height of those 2 points are equal. That's what we expected. And then what's the slope? First of all, what is the slope? Positive or negative? Negative. If I plug -1 into the slope formula, 2 times -1, that gives me -2 over 1. And so now I know the slope over here is -2 over 1. So this little demo is just to show you what these formulas do for us. The original formula for the function told us the height of the parabola at any given point. But the derivative formula, 2x, calculates the slope at any given point. I think that's all I really have to say about this particular example. The key thing is that if you choose any point on a parabola, so any points at all, let's say you go all the way over to x equals 12. Okay, so way up here on the parabola. F of x equals x squared is going to tell you how high that point is. And then f prime of x equals 2x is going to tell you the slope at that point. And we did all that by calculating this definition. What questions do you want to ask before we keep going? Because there's a sudden silence in the room. I'm just not sure how to interpret it. Does everyone feel okay with what we just did with that calculation? Maybe that's the wrong question. It's weird at first. When you do these calculations at first, it's a lot of variables, very few numbers, and it can feel awkward. Yeah, it can feel awkward, and that's absolutely true. So, hey, I'm going to leave that one up there so we can see it, and I'm going to go ahead and move on to our next example. So I'll leave that down there, and I'll just climb up there. Okay, so let's try this again. What I've given you up there is a formula, f of x equals 3x squared minus 4x plus 7. And we'd like to find the derivative formula. That is the derivative. That is a formula that tells us the slope at every given point on that function. All right, so there we have it. Everyone, whenever you do a derivative, you're always going to start by writing the definition first. So we're going to start by writing f prime of x equals the limit, as h approaches 0, of f of x plus h minus f of x all of h. Remember, this was the definition of the derivative formula. It's just the slope formula in disguise, and the h approaches 0 means we want the slope between 2 points that are infinitely close. That's all this formula says. It says, do the slope formula between 2 points that are infinitely close. That's how you interpret this formula. Okay, now, Ready? Draw one huge fraction line. Do a nice big bracket. And another nice big bracket. Because I want you all to see that the numerator is the function minus the function, right? Yeah, f of something minus f of something. And so a really good practice for starting any slope formula, any derivative formula, is to just start by writing the function twice, here and here. We're going to write it empty. So keep in mind this is 3x squared minus 4x plus 7. We're going to write 3 something squared minus 4 something plus 7. And then we're going to write it again. 3 something squared minus 4 something plus 7. Because after all, that's the structure of the definition. You're going to do f of something minus f of something. So I've already got that written there. F of something minus f of something. And what are we going to plug into the first function? X plus h. So the first one we plug in x plus h. And what do we plug into the second one? Just x. And the denominator is h. And remember our algebraic goal, our big algebraic goal, is that we're going to do lots and lots and lots of crazy algebra in the numerator, and what will we eventually be able to do? Cancel the h. That's the end-all be-all goal, right? We did some algebra in the top, and in the long run, we should finally be able to cancel the h out of the denominator. So that's our algebraic goal. So okay with everyone if I bring this down? Okay, so this is where we are. And we're about to do a lot of algebra. So I'm going to work down from where I am. Does everybody remember what x plus h squared is? We just wrote it down in the previous problem. X plus h squared was x squared plus 2hx plus h squared. Remember that from the previous problem? So now we have to be even more careful now. So this is now 3 times x squared plus 2hx plus h squared. And then we're going to have minus 4 times x plus h plus 7. So notice what we just did here. We FOILed out the x plus h. And now I'm just going to otherwise distribute this minus sign so that we can just write everything out. So then we have minus 3x squared, and then minus a negative 4x. What's minus negative 4x? Plus 4x, and then minus 7. All right, so do you see what we've accomplished so far? A little bit. And we just did a little bit. So we FOILed that part. We distributed the minus downstream there. And so now we have to keep going. What do we do next? Yeah, we'll have to distribute this 3. And we'll have to distribute that 4. Because, you know, right now what we're doing is just algebra. We're just multiplying. We're doing PEMDAS. We're going to combine like terms. We're going to distribute. So now what do we have? We have another big fraction line. Big fraction line. And so now we have 3x squared plus 6hx plus 3h squared minus, okay, now distribute the negative 4. So negative 4 times x is minus 4x. Negative 4 times h is minus 4h. And then we have the plus 7, and then the minus 3x squared, and then the plus 4x, and minus 7. That's all of our h. How does it look so far? Messy and terrible, right? Messy and terrible. I like that good, horrible. Looks awful. But as I said before, it gets worse before it gets better. So now we get to start having fun. What can we do now? We get to cancel a lot, and this is where sound effects are very helpful. I prefer the sound effects. Achoo! So I got to cancel out the 3x squared. What else do I get to cancel out? The 7s. Achoo! What else do we get to cancel out? Yeah, the 4x minus 4x plus 4x. Okay? This is all part of it, right? This is hallmark calculus. It gets worse, and then you get to cancel tons and tons of things out. Okay, so is that everything we can cancel? Okay. So now I can write a shorter fraction line now. I just have 6hx plus 3h squared minus 4h, all over h. You all agree it got better all of a sudden, right? It got better, much better. Okay, now what can we do? Yeah, once again, we can factor out an h. We basically knew ahead of time that that was going to happen because we're doing something in order to cancel the h in the bottom. So we know that since our goal is to cancel h in the bottom, we must eventually be able to factor an h out of the top so that we can, in fact, cancel out the h's. So let's factor that h out of the numerator. So by factoring an h out, we just have 6x plus 3h minus 4. And that's all over h. And again, notice at this point, all we've done is just lots of algebraic manipulation. If we plug in 0 right now, it would still be no good. We'd have 0 over 0. But what we're about to do was the genius of Newton and Leibniz, okay, was the ability to transform that from a 0 divided by 0 undefined expression into something that is defined. And so now we simply have, go ahead and write limit now. Limit as h approaches 0 of 6x plus 3h minus 4. Again, technically we should have been writing limit as h approaches 0 in front of every single one of those. But I just bring it back at the end. Okay, so now what? Now can we plug 0 in for h? We sure can. And which term goes away if we plug 0 in for h? The 3h. Right, if I plug in 0 for h right now, 3 times 0 is 0. And so for one last time, and now we have 6x minus 4. That's it. That's the answer. So notice where we started. We started all the way over here saying f prime of x is equal to this definition. We applied the definition to a particular function. We did lots and lots of FOIL, distribution, combining like terms, canceling, factoring out an h, canceling the h, finally plugging 0 in for h, and whammo, it came all the way down to just 6x minus 4. So what does this mean then? For this particular problem, the function, right, was 3x squared minus 4x plus h. That formula right there tells you the height of every coordinate. Whereas now we just derived, through lots of algebra and cancellation, a new formula called the derivative of prime of x is 6x minus 4, and that is now going to tell you the slope at every h value. Now, other than the fact that that was a lot of, algebra, that's it. That's how you do a derivative. We'll do more. That's the answer. 6x minus 4. What do you notice about the slope compared to the original function? Yeah, it's actually smaller and simpler. Isn't that surprising? This advanced thing that we did, which was finding the slope at every point on the curve, which is very advanced, actually produces a formula that is easier than the original formula. That's very surprising. That's counterintuitive. Because finding the height information, that's what the function tells you. And you'd think that if you wanted slope information, it would require a formula even more complicated than the original formula. But no, it simplifies down to something very nice and elegant. All right, well, folks, we did it. So let me tell you a couple things about this. One, this is the definition of how to find a derivative. And after we do it a couple more times, the good news is you never have to do it again because there's all sorts of shortcuts where you can just find the derivative without doing this process. Okay, so we torture you for a couple days, making you do the long process, but then in like a week or two, you learn all sorts of shortcuts, and you can find any derivative like that by just looking at it. You'll know what the derivative is. So does that sound exciting? Okay, so we're just going to do a little more. What was it? Yeah, we'll do a little more torture. Here's another. Wait, that was number 1. There we go. So here's another one. We'll do number 2, and then we'll try number 3. But then I swear, in the next couple of class periods, we're going to learn a shortcut. Now, how does everyone feel right now? You can share. This is a safe space. What would you like to say about this process that you're learning? If somebody asked you about class today, you go home and somebody's like, so
A lot of rewriting.
a lot of rewriting. That's true. A lot of rewriting. Yeah, you can almost feel a little unmotivating while you're doing it. Like, oh, this is so much writing. I don't want to write it anymore. But you have to, right? You just have to keep writing, keep writing. It's like anything else, like running a marathon. You just keep going. What else do you feel about this process? It is very much. Yeah, it's pretty lengthy. And so as you can imagine, I mean, consider people in the 1600s and the 1700s. They didn't have calculators, they didn't have computers, they were doing all this by hand. So you can see why people might have given calculus, a bad name. Oh, that's hard. Is it hard? No, it's just a lot. That's all. It's just algebra. I mean, this is high school algebra. Honestly, wasn't that high school algebra? That was high school algebra. Calculus is not hard. It's long and it's lengthy with many, many steps. And so that's what you'd say. Okay, so let's try it one more time, folks. Just like anything, the third time's the charm. You'll feel a little better about the whole thing. So let's start by writing down the definition. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So that's the derivative formula, the definition. And now we're all going to make a big long fraction line, a big bracket, minus another big bracket, all over h. And what do we put inside those two big brackets? The function, empty, twice. So the function is 4 minus 3x squared. So first I'll write 4 minus 3 something squared. And then I'll write it again. 4 minus 3 something squared. Right? Because we're doing the function minus the function. So we just write down what the function is twice empty. And then we think about what we're actually plugging in. So in the first one, what are we plugging in? X plus h. And in the second one, what are we plugging in? Just x. I mean, the second one is literally just the function, right? The second one is just 4 minus 3x squared. It's just a function. All right. Well, now this is the part where it gets worse. Right? So that was pretty easy. We just write down the definition. We write down the function. That's the easy part. Now it gets worse. But, I mean, really, what does worse mean? We have to FOIL, and we have to distribute. Right? Isn't that what we're about to do? We're going to FOIL, and we're going to distribute. So it's not terrible. Again, it's just high school algebra. So let's start by FOILing. So we have 4 minus 3. Does everyone remember what x plus h squared is? Yeah, x squared plus 2hx plus h squared. And then we have this part, the minus 4 minus 3x squared. There. So now I have to admit, you might be looking at my work saying, golly, Mr. G, couldn't you have done more right then? All you did was write down what x plus h squared is. It's going to take forever if you only do one little thing. And maybe that's why Rosa said it's a lot of rewriting. But what I really like to do, because I'm slow and I'm cautious, I just do the FOIL, and then after I FOIL, I do all my distributions. So I'm going to distribute my -3, and then I'll distribute the minus. And that'll be my next line of work. See, I like to do one thing at a time. The first thing I do is just FOIL the x plus h squared. The next thing I do is I'm going to write out everything after my distribution. So I have 4, -3 times x squared is minus 3x squared. -3 times 2hx is minus 6hx. -3 times h squared is minus 3h squared. Now, minus a 4, that's just minus 4. And then minus a -3x squared. What's minus a negative? I got positive 3x squared. All over h. Okay, well, that was the end of it getting worse. And that's as bad as it gets. Now, it gets better. So what do we get to cancel? We can cancel the 4. And then what do we get to cancel? Yeah, the 3x squared. And that's all we get to cancel. So now we just have a shorter fraction line. We have minus 6hx minus 3h squared over h. So you've seen this development now a couple times. You write down the formula, you distribute everything, you FOIL everything, you cancel out a bunch of terms, and remember our goal is to cancel the h, because that's the offending term. If I plugged in 0 for h right now, I'd be dividing by 0, and that's undefined. So now what do? We factor out the h from the numerator, so h outside of -6 is minus 3h, all over h. Now that allows us to cancel the offending term. And so now that we're all done with everything, I'm going to bring back the limit term. So limit as h approaches 0 of -6x minus 3h. Did it get better? It got way better. We're not even done. It's still going to get better. What happens now when I plug in 0 for h? 3 times 0 would be 0. So that whole term goes away. And our final answer is just -6x. So again, it's just amazing. It's just amazing that the derivative formula is actually better, cleaner, and shorter than the original function formula. So our original function was 4 minus 3x squared. But now our derivative formula, the formula we derived from that formula, is just -6x. And again, the original function tells you the height of any coordinate, and the derivative formula tells you the slope at any coordinate. So just to convince you how cool this is, I'm going to draw a quick picture of this function. It's that. So there's the graph of 4 minus 3x squared. So let's just try a couple values and see if our formula really worked. What would the slope be at x equals 0? What should the slope be at x equals 0? No, what should the slope be? 0. It's a flat line at the top, right? So the slope should be 0. So what happens if I take my derivative formula and I plug in 0? It really does equal 0. So the derivative really is, that formula here tells you the slope at x equals 0. What if I choose a point over here a little bit? I'll say 1. What should the slope be? Negative. So I'm going to do the derivative formula at -1, and the answer is, wait. Oh, positive 1, thank you. Yeah, negative. So sure enough, I got a slope that was negative. And what is the slope? It's actually -6 over 1. So like I now have magical information. I know that if I actually go to x equals 1, I go right there, the slope of the tangent line really is -6 over 1. Exactly. Okay, what if I choose a point over here at -1? What should the slope be? Positive. And sure enough, if I do f prime of -1, that's -6 times -1, which is indeed positive 6. So now over here, my slope is positive 6. So that's just a little demonstration that the formula really works. This formula, this derivation that we did of the derivative really does, for any x value that you choose, you plug that x value into the derivative, and it's actually going to tell you the slope of the curve at that point. Isn't that neat? That's calculus. Right? I don't know if you're impressed or not, but I mean, that was a big deal a few hundred years ago. All right. Well, what we just did was a bunch of quadratics. Right? Every problem we did so far was x squared. So let's try one that's a little more challenging. That one. Now, is that a quadratic? Definitely not a quadratic. Now let me ask you an important question. Is this one going to be harder? No, it'll just be a little longer, right? Nothing in here is hard. It's not hard, it's just long. You know, it just requires step after step after step after step, but it's like a staircase. Like, you might not like climbing 20 flights of stairs, but it's just stairs, right? It's not like crocodiles. That would be hard. Climbing a flight of stairs with crocodiles. But climbing flights of stairs is not hard, it's just long and tedious. Okay, so here we go, folks. Now, I only have 5 minutes. I do want to start this with you. So let's go ahead and begin by writing down the definition. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. And then remember, once you write down the definition, you do a long fraction, and you do bracket minus bracket over h. And that's the setup. The whole thing right there is like, okay, now I'm ready to apply this definition to whatever function they gave me. The function they gave me is 4 over x. So keep in mind that for the function 4 over x, how would I write that empty? That'd be f of something equals 4 over something. And so that's how I write that empty. So let's plug our empty function into those two brackets. We have 4 over something, 4 over something. And what are we plugging in to the first function? X plus h. And what do we plug in to the second function? X. All right. So what we just did right now is called writing down the problem. Just wrote down the problem. What's the next part? It gets worse. What's the next part? It gets better. All right, so you got 3 steps to this. You write down the problem, it gets worse, then it gets better, and then you're done. Now, this is going to take more than a couple minutes to do, and I only have a couple minutes. So let's talk real quick, since you're about to leave. First of all, we are about halfway through. Yeah, I mean, this is the last long problem. It won't take us long to do these next couple problems after this. So we're about halfway through section, here we go, 2.3. And so then on Thursday, January 31st, we'll finish 2.3 and move on to section 2.4. That'll be totally doable. I think we'll be caught up by that point. So then, in other words, what's due tonight? Not section 2.3, only section 2.2. Wait, is that even fair? That's not fair. We just finished section 2.2 today. Yeah, so no, you all have a huge extension in your due dates. The only homework due today, I think, is 2.1. But wasn't that already due? Okay, so due tonight is 2.1. I'm going to update all these dates online. Next Tuesday, you'll have due 2.2 and 2.3. Okay? So really, everybody, you should go home tonight and finish 2.1. Make sure you're all done with that. Now, when you go home and you're doing your homework, I sure hope that you email me. Well, I don't have more up right now, but I sure hope that you email me. I'd say about 4 of you are emailing me with any regularity. And the other 4, I don't know where you are. You're just going home and doing your homework, and I suppose that's great. But I really encourage you to email me because that's what you pay me for. This is what a teacher is. A teacher is 24-hour access to help. You know, that's just my opinion. But when you have a teacher, they're your teacher 24 hours a day, not just during class time. So when you go home and you have a question, you should be emailing your teachers because you pay them for that. Right? Does anyone agree with me? Am I just talking to myself?
I agree with you, but there's people that are like, oh.
You email them anyway. You just keep emailing them until they email you back. Okay, well, does anyone have any questions or needs? Class is out in 1 minute. Okay, well, if you need anything at all, don't finish this problem. Right? Just wait until Thursday. Don't. You know, I don't want you to go home and feel frustrated. Please do not attempt that problem. Just wait until you come back. And of course, everybody, please go home and watch the video because we've now covered everything today that I covered in the video. So if you go home, watching the video will be easy. It'll be a breeze. You'll be like, yeah, I did it. So go home and watch that video. And I'll make sure I post it online. Oh, I already did, actually. Yes, I already did. It's under announcements. If you go to announcements, you'll see the video I posted. How many of you agree with my wife that this is a Christmas tie?
It doesn't really look like a Christmas time.
No, yeah, it probably is a Christmas tie. I think the Santa hat kind of nails it. See you, Josh. Hey, Josh, thanks for your questions. Really fun.
Yeah, I think Tucker has presents sometimes, but he's wearing a Santa hat.
You what?
He has presents sometimes, but the hat is like that.
Yeah, it kind of throws it over the edge.
But like if it's there, you'll
if I
know
said
it's like a Christmas time. But like how would you?
I'm trying to figure out what it was.
You what?
Trying to figure out what it was.
I thought like Pokemon or like those kind of.
This is part of my effort to deconstruct Christmas. Christmas can be all times of year. And you can wear a Santa hat, and it doesn't necessarily mean it's Christmas. You just want to wear a Santa hat. I mean, come on. What, Henry?
Which one do you want?
Exactly. Who wouldn't want to be warm?
Can I follow you to your hours?
Yeah, of course. See you, JR. Boy, that monster drink smells